Hi, we'll look at this geometry problem now. This is a chord of constant length that slides around in a semicircle. The midpoints of the chord and the projections of its ends upon the base form the vertices of a triangle. Prove that the triangle is isosceles and never changes its shape. Now, let's draw the figure and try to understand what is happening. Here we have a semicircle here, and xy is the chord, and the chord is sliding on the semicircle. So the position of xy could change. So in a different orientation, you could have xy somewhere from here to here, right? Okay, so right now let's focus on this figure. M is the midpoint of the chord xy, right? And we are drawing projections of the endpoints of the chords upon the base. So the base is the diameter AB, and we are drawing projections from x and y on the base. So the perpendicular line from x meets AB at C, and perpendicular from y meets AB at D. So these are C and D points. These are projections of the ends of the chord. What he's saying here in the problem is that the midpoint of the chord, which is M, and the projections of the ends upon the base, which are C and D, form the vertices of a triangle. So which is the triangle? It is triangle MCD. The first part of the problem is pretty easy. We have to show that the triangle MCD is isosceles, right? So let's think about how we prove that. So think of the line XC and YD. The line XC and YD basically are parallel, right? Because they are both perpendicular to the same line AB, right? Similarly, if I draw projection from M, so MN is also parallel to XC and parallel to YD, because again, MN is also perpendicular to the same line AB, right? So we can say that for the parallel lines XC, MN, and YD, the two lines XY and the line AB are transversals. Right? So that means that since these lines are parallel, the ratio in which MN cuts XY and CD in the same ratio, right? Mn will cut xy and cd in the same ratio. That is obvious because the lines are parallel and there are two transversals. So xm by my should be equal to cn by nd. And now we know that xm is equal to my because m is the midpoint of xy. So therefore cn is equal to nd. So basically we have shown that n is the midpoint of this, right? Now, if n is a midpoint and it is also perpendicular, so it is like an altitude that bisects the other base, right? The altitude of triangle MCD is bisecting the base. So you can show it very easily that the triangle MCN and the triangle MND, these two triangles are congruent. They are congruent by SAS congruency. And therefore, because they are congruent, MC must be equal to MD, right? So if MC is equal to MD, we have shown that triangle MCD is isosceles. So think about what we have used to prove this. We have basically said that the lines are parallel, the three lines are parallel. So the ratio in which they cut the two transversals will be same. So therefore, N is the midpoint of CD. And if N is the midpoint of CD, the triangle MCN and the triangle MND will be congruent triangles by SAS congruency. And therefore, MC is equal to MD and triangle is isosceles. Now we come to the second part of the question. The second part of the question is a little more trickier. We have to show that no matter what happens to the position of the chord, xy could be like this, xy could be like this, xy could take any possible position, the triangle MCD never changes its shape, right? The triangle is always congruent. Like all the triangles that are formed like that will always be congruent, right? Okay, so let's do that on the next screen. So we'll say this is the situation and let's complete the circle like this. And we'll redraw the same figure. This is A, B, and this is X and Y. And this is my midpoint M. And we had drawn perpendicular like this. This is C, perpendicular like this. This is D. and perpendicular like this was N. And we wanted to show that the triangle MCD is always the same. It is not going to change its shape regardless of the position of XY, right? So how do we show that? We can show that by proving that the angle MCD remains constant. Because if the angle MCD remains constant, then because the triangle will always be isosceles, then angle MCD will be equal to angle MDC, and therefore all angles of the triangle remain fixed, right? So basically, what am I trying to do? I'm trying to show that even if XY was in a different position, angles of the triangle remain same. So that would mean that it would remain similar in shape. So it will always be similar to the original MCD that we have drawn here, right? So I want to show that angle MCD remains unchanged, or that is another way of saying that would be angle XCM is unchanged. XCM is this angle, MCD was this angle. So XCM is basically the complementary angle of MCD, right? So if I can show that the angle XCM is unchanged, then that would mean that angle MCD is also unchanged, right? For all positions of chord XY. For all positions of chord XY. If we can prove that angle XCM is unchanged for all positions of chord XY, then it is done, right? So the way to do this is to draw an additional line, extend basically XC so that it meets the circle at this point. Let's call it Z, right? We are just extending XC so that it meets here at Z. Now we will connect this Z to the Y. So let's connect it like this. We can see a big triangle being formed, triangle XYZ, right? Now notice one thing in the triangle XYZ, we know that XC, okay, so what we know here is that the line CM is parallel to ZY. Why do we know that? CM is parallel to ZY because we are applying midpoint theorem. You will realize that this is like the radius, right? This is like the radius and this is like the other radius. So C is the midpoint. C is the midpoint of XZ. And similarly, we can say that we already know M is midpoint. M is midpoint of XY, right? So by midpoint theorem, the line CM and the line YZ will basically be parallel, right? Because they are the lines which cut the two sides of the triangle XYZ into half-half ratios, right? This and this. So since they are parallel, we know that angle XCM will be equal to angle XZY. Angle XCM will be equal to angle XZY. If angle XCM is equal to angle XZY, what is angle XZY? Angle XZY is basically half of the measure of arc XY, right? Why? Because arc XY subtends an angle XZY here. So obviously the measure of the arc would be the angle it subtends at the center C, right? So angle XZY is equal to half of the measure of arc XY, and that is equal to angle XCM. And we know that arc XY's measure will be depending on the length of the arc, right? Depends on length of XY chord, right? So what we are saying is no matter how you slide the XY chord, the arc length will be fixed depending on whether the length of XY was fixed or not. And in the question, it has been mentioned that the length XY is fixed, right? So arc length is fixed. If arc length is fixed, the measure of arc XY is fixed. And half of that, which is angle XZY, is also fixed, which is equal to angle XCM. So now we have shown that angle XCM is unchanged as long as the chord has the same length, right? So that proves our question. Angle MCD remains constant. And notice that here we have used an extension of a line. We have extended a line to meet it at the circumference of the circle, and that is what led us to the solution. Now, another way to show that would be through coordinate geometry. So if you think about it, I will give you an alternate approach for this problem. If you have a situation like this, X and Y here, and it is in a random position, and this is C, this is no longer the center, and this is D, and we have a chord like this. Center is somewhere here, center of the circle, right? Let's call it O. So we'll parameterize the points here. So we'll say this angle is theta, and let's say this angle is alpha, right? So the circle can have radius r, and we can say that y position would be r cos theta, r sin theta, and x position would be r cos theta plus alpha and r sin theta plus alpha, right? And if you parameterize the points like this, x and y, we just want to show that the triangle remains fixed, right? The triangle's position remains fixed. So for that, we need to show that Mn by CD, which is Mn here, and the triangle was MCD. In order to show that MCD is fixed, we just need to prove that Mn by CD is constant regardless of the position, regardless of X and Y's location, right? So this is like saying the angle is fixed. If the ratio of two sides is fixed, the angle of a triangle is fixed, right? So I want to prove this, and I'm going to use that fact now. Now, CD will become r cos theta minus r cos theta plus alpha. You can prove that using simple geometry, and Mn will become r sin theta plus r sin theta plus alpha by 2. I'm leaving the steps for you. You can try this out, and you just have to prove that Mn by CD, this is Mn by CD, which will come out to be basically sine theta plus sine of theta plus alpha by 2 times cos theta minus cos of theta plus alpha. This part, if you simplify this, this becomes 2 sine theta plus alpha by 2 cos of alpha by 2 divided by 2 into 2 sine theta plus alpha by 2 and sine of alpha by 2. This part gets cancelled, and you are ending up with cot of alpha by 2 by 2. Mn by CD is coming out to be this. Now, remember that this is coming independent of theta. Independent of theta. So independent of the initial position of the y vertex, right? Theta can change and the chord will slide across the semicircle. But my final Mn by CD thing is coming as independent of theta. It only depends on alpha, where alpha decides how long the chord is, right? Alpha angle is deciding as how long the chord xy is. So basically it depends on the length of the chord, but doesn't depend on the theta, which is the initial position of y. So that is an alternative approach to solve the problem using coordinates. However, the geometry approach is much more cleaner and much faster. You have to just hit upon the right idea where you extend the line and you are able to prove that the angle XCM is constant. I hope this problem teaches you something, and you can see that there are alternate ways to solve the same question, right? You can use either coordinates or you can use geometry. So if you like the content, please subscribe to the channel, share it with your friends, and I'll see you in the next video.